In this second video, we're going to continue on our discussion about functions of two variables and optimization of functions of two variables. So we talked about at the end of this first video that a critical point is a point where the first derivative, which is the gradient vector, is vertical, which means the first two components, the normal vector to the tangent plane was vertical, and the first two components of that are actually the components of the gradient vector. So the gradient vector, which is the derivative of a function of two variables, should be equal to the zero vector, which means both components are zero. So if you have a critical point, what does that mean? The definition of a critical point is a point such that the gradient is equal to the zero vector, meaning both partial derivatives are equal to zero, or that one or more of those partial derivatives do not exist. So either the partial with respect to x or y does not exist. All right, now we're going to get into how we find functions, relative minimums and maximums now, which are going to come from our critical points. All right, so we're going to have some similar results to what we saw from Calculus 1 discussed in the first video, in that if you have a max or a min, then your gradient vector is going to be zero, which means both partial derivatives are going to be zero. So if you have a max or a min, then if you're at a max or a min, then you're at a critical point. Okay, if your gradient is equal to zero, as we said in the definition, then you're at a critical point. However, we got to be a little careful. Just because the function's gradient is equal to zero, meaning both your partial derivatives are equal to zero, that does not guarantee we have a max or a min. We have to do a test, which is going to be the second partials test, and we'll get to that shortly. But let's do an example to illustrate that. So let's take a look at this function here. I'm going to go below here and compute the partial derivative. So the partial with respect to x is 4x, and the partial derivative with respect to y in this case is negative 10y. Now, if we want to find the critical points for this function, well, first off, the partial derivatives are always existent. They're polynomials. So there's no issue of whether or not the partial derivatives exist at a given point. So we really need to know, when is the partial derivative going to equal zero? All right, so then all we need to do is just set each one of these equal to zero and solve that system of two equations and two unknowns. And these are very simple equations to solve. We get x is equal to 0 and y is equal to 0. So the only critical point for this function is 0, 0. However, as we'll look at graphically in a moment here, this function does not have a local minimum or local maximum at that point. So let's take a look at that graph. And I've got this plotted using Paul Seeberger's CalcPlot 3D app. But so we've got the graph here, and here's the origin, and we can see this is not a local minimum or a local maximum here. If we go in certain directions, we go up from the origin, but in other directions we go down. All right, so that's graph is an example of what we call a saddle, and the origin in this case is what we call a saddle point, because there's some directions which we're going to increase and other directions for which we're going to decrease. So it's a critical point, yes, but it's not a minimum or a maximum, not a relative minimum or a relative maximum. Yes, and this is an example of a graph which we've seen before. We call that a saddle because it looks like a horse's saddle, or if you've ridden a horse. All right, so here's the definition of a saddle point, and that's going to be one of the possibilities we're going to encounter. A saddle point is a critical point, meaning both the partial derivatives are equal to 0. Small typo here. This is supposed to equal 0. But the function does not have a local extremum, not a local min or a max. All right, so let's take a look at then our second partials test. So this is an extension or an analog to the second derivative test from Calc 1. It's a little more complicated. All right, so we have to assume that the function is twice differentiable and that its partial derivatives listed up here are all continuous. So we got to have the partial derivative with respect to the second partial derivative with respect to x, the mixed partial derivatives, and the second partial with respect to y are all continuous around the point we're focusing on. We're also assuming we have a critical point for which the first derivative, or the partial derivatives, are equal to 0, and we're defining this special quantity which we're going to call capital D and it depends on which point we're plugging in. So we're going to plug in the ordered pair A and B to get a numerical quantity on the right-hand side. So we have to take the double partial with respect to x, multiply it by the double partial with respect to y at AB, and subtract off the mixed partial derivative squared. And then the second derivative test tells us the following things. If that quantity, that number d, is positive, and on top of that, the second partial derivative, so we're looking at option 1 here, and then on top of that, the second double partial is positive, roughly speaking, that's saying that the graph is concave up locally, then we have a local maximum, or local minimum, pardon me, at the point AB. So the function value f of AB will be a local minimum. All right. If also, and then we're moving on to option 2 for local maximum, if that quantity, that number are we computing, and that expression there, capital D, will be a numerical value, it'll be a number. If that's positive and the double partial with respect to x or y, you can do either one, and I'm phrasing it in respect to x, is negative, then what does that mean? We have a local max, and that's because, locally speaking, we're talking about the graph being concave down. If this number comes out to be negative, then we get a saddle point. All right, so then that's going to, the second partials test will detect a saddle point. All right, if that number capital D comes out 0, that's the only other possibility, positive or negative or 0, then we can't say anything. We might have a max or a min. We might have neither a max nor a min. All right, let's go back to the previous example, and let's just illustrate how to apply that second partials test. We'll have some other examples in other videos. So going back to this example, what will we need to look at here? Well, looking at this, we know the only critical point is at 0, 0. All right, if we take the second partial derivative with respect to x, we get 4. If we take the second partial with respect to y, we get negative 10. If we take the mixed partial derivative in either order, the partial derivative with respect to x, then y, we get 0. If we do it the other way, the partial derivative with respect to y, then x, we also get 0. So what is the number for this example, capital D, come out to? Let me just make myself a little bit of space here. Well, we have to we know our critical point is 0, 0. We need to now write out that expression. All right, so what is capital D? Again, it's the double partial with respect to x times the double partial with respect to y minus the mixed partial derivatives, and those will be the same in either order, squared. So we just got to put those in. The double partial with respect to x we saw was 4. The double partial with respect to y is negative 10. The mixed partial was 0. So this quantity, d, which does depend on x and y, or can depend on x and y, I should say, it doesn't in this case. It comes out to be constant. It comes out to negative 40. So in particular, if we go to plug in the critical point that we have, which is 0, 0, we're going to get that constant value, negative 40. All right, so it's negative, and therefore we have a saddle point. That's what the second partial derivative test tells us. All right, and that's going to be our main tool in Calculus 3 for detecting or finding local or relative minimums and maximums. We're going to have other methods for finding absolute minimums and maximums. All right, a couple of comments that we have below here, saying that the gradient 0 really is saying that the derivative is 0. All right, we've mentioned that before. It turns out that for functions of two variables, the second derivative is a 2 by 2 matrix. All right, this is a little bit beyond the scope of the course, but something worth mentioning. All right, because you might see this in differential equations, or if you've had that course already, you might have already talked about 2 by 2 matrices and determinants, and we've actually done that a little bit in Calculus 3 in dealing with vectors and the cross product in some area formulas. All right, but that second derivative turns out to be a 2 by 2 matrix, which contains the mixed partial derivatives in there, and we know how to compute that determinant. We multiply down the main diagonal, subtract off the off diagonal. It turns out that that determinant is equal to that quantity d up in the second partials test. All right, so how do we find relative minimums or relative maximums, or local minimums or local maximums? Well, these are our steps. All right, we don't have a analog to the first derivative test, we're going to be relying only on the second derivative test. So what we do is find all the critical points by taking the partial derivatives and setting them both equal 0. That is a system of two equations, two unknowns, as we saw in that example we did. And this means two different things. It means the partial is with respect to x is equal 0, and separately the partial with respect to y is equal 0. Solving that system of equations gives you the critical points. All right, we also maybe have to look for where the partial derivatives don't exist. All right, but mainly we're going to be seeing where they're going to be equal to 0 to find local mins and maxes. All right, then we're just going to apply the second partials test to classify them as relative or local maximums, minimums, or possibly saddle points. And maybe the second partials test sometimes will be conclusive for us. So that's going to be our process. Again, take the derivatives, set them equal 0, apply the second partials test, second derivative test. All right, that's for finding relative mins or maxes. All right, now let's a couple of things to note here. We might not have a max or a min. If you have a function which is on a region of infinite size, say the whole xy plane, then you could have a function like this one which goes up forever and then also goes down forever. All right, you may not attain an absolute max and an absolute min. But if we have a function, a continuous function, and it's restricted to a closed bounded region in the xy plane, we're always going to attain a max, an absolute max and an absolute min. All right, again, absolute max and absolute min means the highest and the lowest point. A bounded region is closed if it contains its boundary points. Okay, same thing for a curve. If it's a closed curve, it's going to contain its max and a min. How do we do optimization over closed bounded regions? Well, there's only a couple of possibilities, very similar to what we saw in Calc 1. Either you're going to have the maximum and minimum, the absolute max and min happening at one of the boundary points, or it's going to happen at an interior critical point. So we go through these following steps. We find the critical points like usual. All right, then we're going to try to restrict our attention to the boundary and find the largest values of that function relative to the boundary, and then just see which are the biggest. All right, evaluate the function at the critical points found in step 1 and also the boundary candidates in step 2, and then that will find us the absolute min and max. Again, that's for a two variable function over a closed bounded region. I've got a picture to go with this down here below. This right here is really the graph of this function f of x, which is f of xy, which is x times y, and it's really restricted to the unit disk. So we're talking about inside the unit circle, including the boundary. That's the graph there. We can see there's a highest point on the graph, and it's obtained in two different places. All right, we've got the highest point happening here and here. There's an absolute minimum, which is happening actually in two different places. All right, continuous function, a closed bounded region has to attain an absolute max or absolute min. All right, and we're going to be finding those. Quick remark, which is again similar to what we had seen in Calc 1, we don't need to apply the second partials test or the second derivative test when we're finding absolute mins and absolute maxes. That's only for relative or local mins and maxes. Okay, just to wrap up this video, we're also going to look at what happens when we take a function and restrict it to a curve, and we've done this in multiple contexts in previous work. If you have a continuous function which is restricted to a closed bounded curve, all right, and that has finite length, then you're going to attain an absolute max or an absolute min. So I've got an example here. We can see it's got a highest point and it's got a lowest point out here. But if you restrict a function, continuous function, to a curve that has infinite length, all right, so that would be maybe the image of your restrictive function in the xy plane that has infinite length. That maybe is its graph. If you restrict it to a curve of infinite length, you may or may not obtain an absolute min or an absolute max. We can see this graph is going up forever and maybe goes down forever as well. So we just got to be careful of that. All right, how do we do optimization for function restricted to curves? Well, we can optimize the scalar function using single variable calculus results. All right, and then, or the other option, which we'll discuss in the next section, is possibly using the Lagrange multiplier method.